In this unit, we're going to look at electrochemistry, and this is based on oxidation reduction or redox reactions. There's actually a large variety of different reactions that fit into this particular category, but they all involve the transfer of electrons from one reactant to another. And so I have a few pictures here of just some of those different types of redox reactions. So a lot of different biological processes are actually considered redox reactions because there's a transfer of electrons involved. So this is just a picture of cellular respiration, more specifically the electron transport chain. So of course that involves the transfer of electrons. Two more common examples are combustion as well as corrosion here in the upper right-hand corner, rusting. So these involve oxygen and the transfer of electrons from the substance that's either burning or that is corroding to that oxygen. And the last example that I have here is a fuel cell car. So a fuel cell is a battery. So this is really an electric car. And the fuel cell, it is actually being fueled here. In this example, you're inputting hydrogen. What it does is it provides electrons that actually can be used to power the car. It's electrical circuitry that makes the wheels actually run. So batteries are a great framework for actually looking at redox reactions. Every redox reaction is made up of two parts. You have oxidation and you have reduction. So we'll look a little bit more in depth at what those two parts involve in just a few minutes. But essentially in a battery, what we do is we actually physically separate those two halves of a redox reaction, and we allow the electrons to be transferred separately from one half to another so that it can actually go through an electrical circuit and do work for us. So this is a diagram of a simple fuel cell, and it's a nice way to actually see the separation of oxidation and reduction. So in a fuel cell, our fuel is actually hydrogen gas, and it is actually passed over in that fuel cell. It's passed over an electrode, which facilitates the loss of electrons by that hydrogen gas to form hydrogen ions, H+ ions. So this is known as oxidation. This is our oxidation half reaction. It's the loss of electrons. All right. Now, those electrons are actually separated from the hydrogen ion products and funneled through an electrical circuit, which does work for us. Now, after they pass through that electrical circuit, they are transferred back to another electrode. The hydrogen ions, the other product of that oxidation process, are actually transferred also to that electrode, that second electrode, but they are passed through an electrolyte medium that will allow them with the electrons to recombine along with the other reactant in the net process, which is oxygen gas. So the oxygen is cycled in from the air and passed over that second electrode in that second half cell. And it, along with the hydrogen ions and those two electrons, recombine to form H2O. Now, the net process is just hydrogen gas plus oxygen gas produces H2O. But when we actually conduct that reaction through a fuel cell where we have physically separated those two halves, the oxidation half where hydrogen loses electrons and the reduction half where oxygen gains those electrons again and combines with those hydrogen ions, we actually allow those electrons to move separately and do some work for us before they're actually transferred. But the net reaction is just the transfer of electrons from that hydrogen to that oxygen gas to produce water. It's important for you to know these two terms, oxidation and reduction, and what they mean in terms of the transfer of electrons. So I have a little mnemonic for you guys to remember what these terms actually stand for. It's Leo-Ger. So Leo for the lion, Ger for the sound he makes, right? So Leo stands for loss of electrons equals oxidation. And in any oxidation half reaction, you have a reactant that is losing electrons. And what this means ultimately is that electrons are going to be on the product side of our half reaction, of our oxidation half reactions. GER stands for gain of electrons equals reduction. And in any reduction half reaction, the reactant is gaining electrons. And so you're going to find that the electrons are going to be on the reactant side of the half reaction. Now, as we continue to explore redox reactions and how that transfer of electrons can be utilized to actually do work, we need to be able to break apart our redox reactions and actually see what is oxidation and what is reduction. And so the first thing that we're going to focus on is really how to balance oxidation-reduction reactions. There's a little more to it than what you may have learned in the first semester of general chemistry. So we have to do a little bit more than just balance in terms of mass or number of atoms. Redox reactions have to be balanced in terms of mass and charge. And that process of making sure that charge is balanced ultimately means that you are making sure that the number of electrons that are produced in an oxidation half reaction, it's the same number of electrons that are gained in a reduction half reaction. So to make sure that that's what's happening, you actually have to separate any particular redox reaction into its two half reactions to balance it appropriately. So I'm going to give you guys a series of steps that you can use to break apart any redox reaction into its halves, and then make sure they're balanced for both mass and charge before you add them back together again. We are going to look primarily at aqueous reactions, so those that have the majority of your reactants and products are actually dissolved in water, or AQ. And we can classify these into three basic categories or broad categories. So we can talk about simple redox reactions. And by simple, I just mean that there's no oxygen or hydrogen involved as a reactant or product. So it is just, in this case, the example that's given here, we just have tin and iron as our reactants and a different ion charge for tin and iron on the product side. There's no oxygen or hydrogen in that formula. Now, if oxygen or hydrogen is actually found in any of those reactants or products, so here you can see it's in the permanganate ion, it's also in the other reactant, the oxalate ion, and our product CO2. If you find oxygen there, it can be a little trickier to balance for both mass and charge to keep both of those together. So what we find is that we can actually use the water that the reactants are dissolved in to help us with that balancing process. But it is going to matter in those cases whether it's a little bit acidic or a little bit basic solution that your reaction is actually occurring in, because the presence of hydrogen ions and hydroxide ions can influence your charge balance. We're going to start for this particular video with those simple reactions so that we can focus primarily on the process, and then we'll add in the oxygen in the next series of videos. So the first step in balancing any redox reaction is actually to take the net reaction that you're given to balance and break it apart into two half reactions. We're not going to worry about oxidation and reduction at this point. All we want to do to break those into half reactions is just take the different reactants and actually separate them into half reactions, and the product will be whatever those reactants become. So for example, I have two reactants in this particular equation. I have tin and I have iron. These are going to be my reactants in my half reaction, my two half reactions. And on the other side, on the product side of these two half reactions, I'm going to take whatever the products are that we find tin and iron in. So tin 2 plus must have become tin 4 plus on the product side. That's where I find it here. And I find iron in the form of an iron 2 plus ion. So that's what I put for my product in the second half of that. Okay, it's really important that when you do this, you make sure that you get the correct formulas, the chemical formulas, as well as the correct charges, because we are going to be balancing this in terms of both mass and charge. Now, once we have those separated out, we are going to start with the mass balance. So this is the same as what you did in the first semester of general chemistry, where you just made sure you had the same number of each type of atom on each side of the arrow. So in this first half reaction, I have one tin ion here on the left and one tin ion here on the right. Well, that's 1 and 1 for tin. So that's mass balanced. Now, I do recognize that they have different charges, but charge does not influence mass. So we're going to ignore the charge when we're doing our mass balance and just look at the actual elements and make sure that we have the same number of each on each side of the arrow. So tin is mass balanced. And it actually turns out for this example that my second half reaction is also mass balanced. I have one atom of iron and one atom of iron on the right-hand side as well. Different charges, but it's still iron. So it's still the same mass as long as I have the same number of atoms. Okay, now once you ensure that your two half reactions are mass balanced, we're going to actually balance these in terms of charge. And what that means is we just want the same total charge on each side of the arrow for each of these half reactions. So I have a +2 for that first half reaction on the left-hand side and a +4 for that charge on the right-hand side. Well, that's very obviously not the same. In order to get them to be the same, the only thing I can do is add electrons. And since electrons are negatively charged, I am always going to add those electrons to the more positive side of the half reaction. So between +2 and +4, well, +4 is definitely more positive. So this is the side I'm going to add my electrons to. And I'm going to add however many electrons I need to bring down that more positive charge to the same charge as the other side. So I'm trying to go from +4 to +2. I need 2 of those negatively charged electrons. And now, on this product side, in order to look at that total charge, I'm going to add together the charges of everything, all of the different products that I see here. And so I'm just going to write these charges again over to the other side so that you can see this. We go from +4 for my one ion of tin on the product side. And I'm going to add to that the charges associated with those 2 electrons. So it's 2 times -1 for each of those electrons. Well, +4 plus 2 times -1 is going to give you a total charge on the right-hand side of +2. And that matches perfectly our total charge. We've only got the one ion on the left-hand side is +2. So this is charge balanced. Now we're going to do the same thing for the second half reaction. I'm comparing +3 for my iron on the left-hand side and +2 on the right-hand side. And +3 is definitely more positive. So we are going to add electrons to the +3 side. And this time I only need 1 electron. +3 plus a -1 for that 1 electron is going to get me a +2 total charge on the left-hand side to match the +2 charge on the right-hand side. And now both of these half reactions are charge balanced as well. Okay, so I'm just going to erase this to give myself a little bit more space to work. Now, we have mass and charge balanced our 2 half reactions individually. But to finish our balancing process, we have to add these 2 half reactions back together. And when we do that, all the electrons that were produced in one half reaction have to be consumed in the other half reaction. So our next step is actually going to be to balance the electrons between the half reactions. So they'll cancel out when we add them back together. Now, before I do that, though, I should point out to you guys, we actually have enough information now to assign these as either the oxidation or reduction half reaction. So in oxidation, you lose electrons. Well, that means the electrons are always going to be on your product side. So whichever half reaction you had to add electrons to the product side is going to be your oxidation half reaction. And in reduction, you're gaining electrons, so that means they're going to be on the reactant side. And whichever half reaction has the electrons on the reactant side will be your reduction half reaction. And I should note, as a troubleshooting, a way to sort of check yourself as you are doing your balancing for redox reactions, when you are done with the charge balance for each of your half reactions, you always should have electrons on the product side of one half reaction and on the reactant side of the other half reaction. If you find that you've managed to put the electrons on the product side of both of your half reactions, something is messed up in your balancing process, okay? They have to be on opposite sides of the arrow for those two half reactions if you've done it correctly. All right, now before we can add these two back together, we want them to cancel out, but we need to make sure that we get the same number of electrons on those opposite sides. So I have 2 electrons in the first half reaction and only 1 down here. If I add these together, only one of these electrons is going to get canceled out. If I want both of them to get canceled out, well, I need to increase the number of electrons in the second half reaction to 2. I can do that, but I have to make sure that I don't mess up the mass and charge balance that I've already got there. So the only thing you can do to increase the number of electrons, once you've done that mass and charge balance, is to multiply everything in that particular half reaction by 2. So what this becomes, I'm going to write it over here, you end up with iron with a 3+ charge. Oops, you end up with 2 iron. That 2 is going to be multiplied before every single term in this half reaction. Plus our 2 electrons. And on the product side, we have 2 irons with a +2 charge. Okay, we're going to add this half reaction to the first one. So I'm just going to actually move the first half reaction over here so they're on top of each other. So that's tin with that 2+ charge becomes tin with the 4+ charge plus my 2 electrons. And we'll add them together. And when we add them together, just like when you've added any set of reactions together, right, you can cancel out anything that occurs in the exact same form on opposite sides of the arrow, as long as they're the same number. So I've got 2 electrons on the product side, 2 electrons on the reactant side in the next reaction. They cancel each other out. And I'm going to bring down everything else that doesn't cancel. So that leaves me with tin 2+ plus 2 iron 3+. And on the product side, I've got tin 4+ plus 2 iron 2+. Okay. So that's my 5th step. You add your half reactions, canceling the electrons in the common species. Now, this should be my final balanced half reaction, excuse me, my final balanced net redox equation. But it's always nice to be able to do a final check. And so your final check is just make sure that you've got the same number of atoms of each type. Your mass balance is still held true, as well as your charge balance. So the total charge you have on each side of that arrow is still the same number, the same total charge. So in terms of my mass balance, I've got 1 tin and 1 tin still, and I've got 2 irons and 2 irons. Now, in terms of that charge balance, I'm just going to write the charges down here. I have a +2 for that 1 tin, and then I've got 2 irons, each with a +3 charge. So +2 plus 2 times +3, that is +6. So this, as a total, gives me +8 on the left-hand side. On the right-hand side, I've got +4 for that tin, plus 2 of those irons, each with a +2. Well, again, +4 plus 2 times +2 is going to give you a total of +8. So it is charge balanced. I've got the same total charge on each side of that arrow. Let's look at one more simple redox reaction. So here we're going to look at iodine plus chromium 2 plus reacting to form chromium 3 plus and iodide ion. We're going to follow the same steps. We're going to first separate the reaction into half reactions. So we're going to take each of those reactants and pull them out and put on opposite sides of the half reaction arrows what they become. So iodine must become iodide. The second half reaction, we've got chromium 2 plus, our other reactant here, and what it becomes, which is chromium 3 plus. Okay. Next, we're going to balance those half reactions by mass. And in this particular example, we actually do have a little bit of mass balancing to do. That first half reaction, I have 2 iodine, but only 1 iodide ion on the other side. So I need to have the same number. So we're going to do the same thing that you would do anytime you're balancing by mass. The only thing you can do is to add coefficients to the side that needs more to bring up the number of atoms. So I need 2 iodide on that side, so I'm going to add the coefficient of 2. It's really important to do this step first because it will affect your charge balance. If I increase the number of a charged ion, it's going to affect the overall charge on that side. So it's really important that you remember to do your balancing by mass first. Okay, my second half reaction is already balanced in terms of mass. The charge doesn't affect mass. It is just the number of atoms and of each element, and I've got 1 chromium and 1 chromium. Okay, the third step is then to balance for charge. And we're going to do this by adding electrons to whichever side is more positive. So for our first half reaction, we've got a total charge here on iodine, I2. That's actually neutral, right? There's no charge written up here in the right-hand corner, which means that this is a neutral compound. So we have a charge on this side of 0. It's supposed to be a 0 there. Okay. That's in contrast to the other side where we've got 2 negatively charged iodide ions. So that's a charge of -2. Well, in a comparison of 0 versus -2, 0 is more positive. So this is the side that we are going to add our electrons to. And that means in order to bring it down to a -2, and again, it has to be -2 because I've got 2 of these iodide ions, I need 2 electrons. And now that half reaction is actually balanced. Okay, the second half reaction is a little bit simpler. We've just got +2 on this side and a +3 on this side. The +3 is the more positive side, so that's the side we're going to add electrons to. And I only need 1 to bring +3 down to +2. Okay, and now that I've added my electrons, I can also identify which one of these was oxidation and which one was reduction. So oxidation is always the loss of electrons, so it's always going to be the half reaction where electrons are on the product side. So this time chromium is my oxidation and iodine is my reduction half reaction. We have balanced each of those half reactions individually in terms of charge and mass, but now we have to balance the electrons between the half reactions so that when we add them back together, the electrons cancel. Okay, so I have 2 electrons in that first half reaction. I have 1 electron in the second half reaction. I need to raise that smaller number of electrons up to a larger number, hopefully the same number as this. I can very easily bring 1 electron up to 2 by multiplying this by 2. I just have to remember I have to multiply everything in that equation by 2 so that I don't mess up the mass and charge balance that I just did. So this is going to end up becoming 2 chromium 2 plus goes to chromium 3 plus 2 chromium 3 plus 2 electrons. And I'm just going to carry over the other half reaction, even though it doesn't need any coefficients multiplied through. We're just going to have that as I2 plus our 2 electrons goes to 2 iodide. And now we can do the next step, which is just to add these two half reactions together, canceling out the electrons and any common species. Okay, so in this particular equation, it's only electrons that occur on opposite sides of the arrow in our two half reactions. So, and we have the same number. We made sure to have the same number so that we could cancel them out. And that means we just carry everything else down, and we've got I2 plus 2 chromium 2 plus goes to 2 iodide plus 2 chromium 3 plus. Okay, and it's always a good idea just to double check. We've got a mass balance and a charge balance still. So the mass balance, I have 2 iodide, 2 iodide, 2 chromium, 2 chromium. The charge balance, my iodine, the I2, again, is neutral because there's no charge written up in that upper right-hand corner. My chromium on this side, I've got 2 of them, each with a +2 charge, so that's 2 times +2. That is going to give me a total charge on the left-hand side of +4. On the product side, I've got 2 iodide, each with a -1 charge, plus I've got 2 chromium, each with a +3 charge. So -2 plus +6, that combines together to give me a total charge on the right-hand side of +4. And this is balanced in terms of both mass and charge. In the next PowerPoint, we're going to look at adding oxygen and hydrogen into these redox equations and how we need to balance those.